This is a video presentation of Chapter 5, Section 1 in the 8th grade textbook entitled Ratios and Proportions. Okay, so we've made quite a leap here. We were doing three-dimensional geometry, and now all of a sudden we're talking about ratios. What is a ratio? Well, ratio 2 is going to look like a fraction. Next question, why is this important? Well, we've studied ratios before, so I think you've got a pretty good grasp on what we're doing here. Really, this is just a few sections of review primarily, so I think you're going to find the next few sections rather enjoyable because you should find them really easy. But that doesn't really answer why is this important. Well, where we're going to be heading here very soon is the concept of graphing lines and the concept of slope. And slope is one of the most important ratios when we start talking about pre-algebra and algebra concepts, because we're going to spend a lot of time on graphing lines and working with lines, and if we don't understand a ratio, we're going to be lost when it comes to slope. So we have to make sure we understand a ratio here. So this is just a good chance for us to go over the idea of ratios before we head into the real meat and potatoes of 8th grade math, a lot of pre-algebra and algebra-like concepts when we're talking about slope. Okay, so let's get some definitions out of the way here. Ratio, that's a comparison of two quantities by division. Again, that's kind of a fancy way of saying it's something that's going to look like a fraction. Equivalent ratios, those are ratios that make the same comparison. If you think of equivalent fractions, you're on the right path already. And a proportion is an equation that states that two ratios are equivalent. An equation that states that two ratios are equivalent. So really saying these two fractions are equal to each other. Again, a ratio is a comparison of two quantities by division. An equivalent ratio are ratios that name the same comparison or make the same comparison. And a proportion is an equation that states that two ratios are equivalent. All right, so let's go ahead and start with number 1 here. They're asking us to find two ratios that are equivalent to the given ratio. Now, you've got lots of options in life here. You can, if you want to, take that ratio 9/27 and make it smaller. Reduce it just like you were reducing a fraction. So chopping out 9 there, which is the greatest common factor, or maybe you just make it smaller but you don't take everything out and you divide out 3. Either one of those would be acceptable. You could also make it larger. It doesn't say anything about simplest terms or anything like that, so you can make it bigger by multiplying both the top and the bottom, the numerator and the denominator, by the same number. A lot of the times you're going to see the book multiplying by 2 because it's perceived that that's really easy. And indeed, that's what you see on the first line of work there. They're taking 9/27 and multiplying by 2, top and bottom. 9 times 2 is 18, 27 times 2 is 54. Second option there, they're chopping out 9 because they're taking out the greatest common factor. So I take out 9 there. 9 divided by 9 is 1, 27 divided by 9 is 3, and we end up with 1/3. So 2 equivalent here to 9/27, so it would be 18/54 and 1/3. Now, one point out here that I said like a fraction, it is like a fraction. And I even use the terms numerator and denominator. Technically, it's not a fraction though. And the reason it's not technically a fraction is because you're allowed to have a decimal in the top or the bottom spot, what I would normally call the numerator or denominator. Because of that, it's not really truly a fraction, but it just functions exactly like a fraction. So a lot of the times you'll hear me talk about it like it is a fraction. You'll hear me call it numerator and denominator when I really should be saying here top and bottom because it's not really a fraction. But indeed, it's the same thing as if we were doing things with a fraction, writing equivalent fractions, things like that. So use those same techniques because you already know those techniques, so that should make this all that much easier. All right, here's number 2. We're supposed to simplify to tell whether the ratios form a proportion. Now, there's actually a lot of different ways to do this, but what they decide to do here is say, okay, we want to know if these two things form a proportion, meaning, in essence, are these two things the same thing? And the way they do that in this particular problem is to reduce the fractions down to simplest terms. And if we get the same thing, then the answer is going to be yes, they form a proportion. And if they don't, the answer is no, they don't form a proportion. So with 3/27, what they do is they take and chop 3 out of both the numerator and the denominator here, because 3 is the greatest common factor, and they get 1/9. And with 2/18, they take 2 out of both the numerator and the denominator, and they get 1/9. Well, since both of these reduce down to 1/9, the ratios are a proportion here, or are in proportion. You can say it any way you want. There are other options here. What might be easiest is to take and just divide these out and change them to decimals. And if you get the same decimal, that means they're in proportion. If you get different decimals, they're not. Remember, to change these to decimals, you do top divided by bottom. The other thing you can do, which is something most of you are really familiar with and probably quite good at, is you could write these out with an equal sign between them. And what you would do then is you would cross multiply. And what's going to happen is you're going to get two products there. 27 times 2, which is 54, and 18 times 3, which is also 54. If you get the same number from each multiplication, you have a proportion. And if you get different numbers from those multiplications, you don't have a proportion. And indeed, we see here once again that since the numbers are the same, you do have a proportion which matches the answer we got by reducing. It does not matter which technique you use to prove it, as long as you use one of them and use it correctly. All right, so let's go ahead and take a look at example 3. Example 3 says at 4 degrees Celsius, 4 cubic feet of silver has the same mass of 42 cubic feet of water. At 4 degrees Celsius, would 210 cubic feet of water have the same mass as 20 cubic feet of silver? So, they're asking here, or what they're writing here, is from this first line, that at 4 degrees, you have 42 cubic feet of water. And then they want to know, at that same temperature, would 210 cubic feet of water have the same mass as 20 cubic feet of silver? So notice what they've done here